Guy is the Vice President of Communications Satellite Solutions at Lockheed Martin. He was previously the Director of Space Exploration Systems for Lockheed Martin. It was under his leadership as the MAVEN Flight System Program Manager that the MAVEN spacecraft was assembled, integrated, and tested. Guy is a local product here in Colorado, where he received his bachelor's degree in aerospace engineering from the University of Colorado Boulder. He went on to receive his master's in aerospace engineering from the University of Southern California. But as a current University of Colorado employee, I'm pretty confident that Guy is a Buffs fan when the two Pac-12 teams clash, as they will this November here in Boulder. I won't speak for you, Guy, but I just assume.
Oh, yeah. So you never lose it.
Sounds good. Well, thanks for joining us, and we look forward to your presentation. I think Christine already mentioned if questions come up in the chat, she and I will monitor those and forward those to you as appropriate throughout your talk.
Well, excellent. Thank you, Tom. I'm excited to be here. And first thing I want to do is say thanks to both you and Christine for inviting me to do this. And then also want to throw a shout out to Dr. Bruce Jakowski. He was and is the leader of the MAVEN program. He's a CU professor working at the Laboratory for Atmospheric and Space Physics. And in addition to being in charge of the program, bringing on my organization, Lockheed Martin, to build the flight system, he also produced a lot of the charts that we give in these presentations to the public. So I shamelessly stole a bunch of his charts for this one. So Bruce, if you're out there, thank you very much. The presentation is kind of divided into two sections. We thought it might be interesting to kind of go through my career so people can kind of hear about how do you, what did it take to kind of get to the place where you get to build spacecraft that go to Mars? So I'm going to go to the first slide, and basically, as you pointed out, my career kind of started at the University of Colorado up in Boulder. I went there as an undergraduate, 82 to 86. In addition to getting a great education and having a lot of fun in Boulder, I got an opportunity to work for LASP as a satellite controller. So I actually had a part-time job throughout the year and full-time in the summer, where I got to go in and actually be the person sending commands to the Solar Mesosphere Explorer satellite, which was orbiting the Earth, and CU did the mission operations for them. So I was sending commands, receiving telemetry, and then also doing data processing for various scientists who had instruments on board. So it's a great way to learn about the aerospace industry, about how satellites work, about how they're designed, and really gave me a good background once I graduated for getting a job out in the industry, being ready to go. So CU was a great place to kind of start my career off. Unfortunately, I graduated about a couple of months after the first space shuttle disaster, and so aerospace companies weren't hiring at the time. So,
Guy, this is Tom. Sorry, yeah. It looks. I don't know if you're forwarding your slides. They are not forwarding. Oh. As far as I can see from this end.
Well, let's try the sharing thing again here.
Okay, we're still on your intro slide with the title of your talk.
Okay, let's there we go. How's that?
Give it a second. Right now I'm seeing you, but not your slides. Okay.
Technology is
there we go. Okay, so now it's on the slide with the LASP logo and the SME spacecraft. Perfect. So now it all fits into context.
All right, so hopefully some of these pictures are familiar, or at least some pictures of college and the spacecraft I got to work on, and even the dorm that I spent my first couple years in. So as I was saying, when I graduated, here's my rejection letter from Lockheed and my rejection letter from Martin Marietta at the time. And so not getting a chance to work for those great companies, I actually ended up at the Jet Propulsion Laboratory out in Pasadena, which turned out to be a great place to start my career. Jet Propulsion Laboratory is known for interplanetary spacecraft, And at the time, I got to do a lot of really fun missions. So I got to do the Galileo mission to Jupiter. There, leveraging my mission operations experience, I was the uplink systems engineer working on the software and the systems to send commands to the spacecraft. And I did that for a year preparing for launch. And then we launched, and then I got to be on the mission operations team as we started the spacecraft's journey to Jupiter. And then the next major project I did was Mars Pathfinder. This was a Mars lander in the mid-90s. And it was a fantastic project to work on, especially for a young engineer. The great thing about that project is it was very small, which meant a lot of us 20-something engineers got to have a whole lot of responsibility that in a larger program we wouldn't have gotten. And so I got to be on the spacecraft design team. I was the head of the electrical test program during assembly, test, and launch operations. And then I went into mission operations, and I was actually the mission controller when, on the day we landed on the surface of Mars successfully. So it was kind of a really pinnacle of my career, being able to be part of that team and successfully land on Mars. And that's kind of where I got the Mars bug. And so I ended up doing a whole lot of Mars missions. So I switched over to Mars Odyssey, and at the time, our Mars Odyssey was a JPL program, but the spacecraft was being built by Lockheed Martin's facility here in Denver, Colorado. And so I was the customer representative, where I actually, since I wanted to get back to Colorado anyway, I volunteered to kind of come out here and live with the contractor and help them as they built the spacecraft. So I got to do Mars Odyssey and Mars Reconnaissance Orbiter as a JPL customer rep out here at the Lockheed Martin facility. And then after that, I ended up switching companies and joining Lockheed Martin as an employee of theirs, still working on Mars programs. So I was the chief systems engineer for the Mars Phoenix project, which was another Mars lander, landed in 2007. And after that, I got the opportunity to become the program manager for MAVEN. It was a fantastic opportunity, not only because it was a fun mission to go to Mars, but because it had it was basically being managed by Dr. Joukowsky at University of Colorado in Boulder. So it was a great way to kind of get tied back into my college roots. So I'm going to talk to you a little bit about MAVEN and kind of what the mission was trying to do, kind of focusing in a little bit on some of the engineering challenges. And so for those of you who may not be quite as familiar, the purpose of MAVEN was to go to Mars. It was a Mars orbiter, but instead of previous orbiters, which focused on looking at the geology of the surface of Mars, MAVEN was different. It was going to look at the atmosphere of Mars. And now we know from previous missions to Mars that Mars once had liquid water flowing on the surface. We can see the outlines of ancient stream beds, of ancient lakes, even shorelines of what look like ancient oceans. Rovers on the surface have found minerals and geology that only could have been shaped by water that had been liquid for long periods of time. That's corroborated by remote sensing from spacecraft like Mars Odyssey and MRO, Mars Reconnaissance Orbiter. And so we know that there used to be liquid water on the surface for long periods of time. And the big question, though, is that the atmosphere today is too thin and too dry to support liquid water on the surface. If there was liquid water today, it would quickly flash evaporate. And so today, Mars has a very thin atmosphere, but we know in the past it must have been much thicker, much warmer, and much wetter. And so that's the big science question, is what happened to the atmosphere? And so MAVEN was all about going to Mars and trying to figure out what happened to the atmosphere. So the scientists came to Lockheed Martin. They basically started forming a team to do this mission. They asked the Goddard Space Flight Center in Greenbelt, Maryland, a NASA center, to manage the program. they went out to not only looking inside labs for building science instruments, but also at Goddard to build some science instruments, and at the University of California, Berkeley. So they understood, they knew what kind of science instruments they wanted to do. They wanted a set of stuff to look at the sun and the solar wind, because they believed that had a big impact on what happened to the atmosphere. And then they wanted to look directly at the atmosphere itself with a couple of instruments in the UV and the near infrared. And then they also wanted to look at both ions and ion-related properties and processes, which meant magnetic fields and then and electromagnetic fields around there. And so they kind of had a good idea of what science instruments they wanted to fly, but basically they needed to figure out a way to get those out there and get them in the right position to take that science data, and for that they needed a spacecraft. And so they came to Lockheed Martin, who has a lot of experience in interplanetary spacecraft, and asked us to partner with them. So from an engineering point of view, we had to, we were able to leverage a lot of heritage. So we had been doing interplanetary spacecraft all the way back to Viking in the mid-1970s. And as you can see, we've had a long history of interplanetary spacecraft, more than the rest of the U.S. industry combined. So we've done missions like Magellan, which went to Venus. We've done missions that have gone to the moon, missions that have gone and returned samples like Genesis, which returned samples of the solar wind, Stardust, which went to a comet and returned samples of the comet tail. But one of the things, and then we've also got Juno. We'll throw a shout out to Juno out at Jupiter right now, taking tremendous science and returning that. But one of the things that we're most known for is our Mars missions. So we've been a part of every NASA mission to Mars. For rovers and landers on the surface, we provided the aeroshell structure, basically the entry system, to help get them safely through the atmosphere and down to the ground. But we've also built a lot of the spacecraft ourselves. We've been the prime contractor for a lot of the spacecraft. So not only providing the landers on Viking, but we've done Mars Global Surveyor, we've done Mars Odyssey, and Mars Reconnaissance Orbiter, so a lot of Mars orbiter experience. So that's one of the reasons that Dr. Joukowsky came and wanted us to partner with them, was our extensive Mars orbiter experience. So we started working with them on what do we as engineers need to do to help Dr. Joukowsky get the science that he and the science team wanted to get. So basically he told us about the science instruments, he told us what the science instruments wanted to do, and then we started crafting with him and with Goddard a mission that would accomplish those along with a spacecraft design. So some of the engineering challenges we had was, first off, there was a set of instruments that wanted to look at the sun all the time, monitoring the solar wind and solar output continuously. And then the other half of the instruments wanted to look at the atmosphere. So you have, as you're orbiting the planet, you can imagine from an engineering point of view, how do you keep half the instruments pointed at the sun and the other half looking at the atmosphere as you rotate around the planet. The instruments also, the ones that wanted to look at the atmosphere, didn't want to just look at it from one static altitude. They wanted to basically go all the way into the atmosphere and then take measurements all the way out to where the atmosphere is totally gone away. So go very close to the planet and go very far away from the planet. The other thing they wanted to do is do some in situ measurements, actually go into the atmosphere and take some direct measurements of that. From an engineering point of view, that raises some challenges. Every time you go through the atmosphere, while you're not going very deep into the atmosphere, even the part you're going into is going to have a little drag on the spacecraft, little tug on the orbit. And so every time you go through the atmosphere, it's going to change your orbit. And because these science instruments want to take measurements at very specific times in the orbit, that changes the timing of all those measurements. So we had to figure out a way, how do we figure out how the spacecraft can adjust for all those timing uncertainties as you go through the atmosphere. And then to pile on top of that, we did have a cost cap for the mission, so we had to keep the mission affordable. And one of the things about that was the Deep Space Network. This is the series of ground antennas here on the Earth that's used to talk to interplanetary spacecraft. There's basically 3 station complexes around the world. We have one in Goldstone, California, one in Canberra, Australia, and then one in Madrid, Spain. And there's only those 3 sites, and there's a lot of interplanetary spacecraft out there. So to keep cost affordable, the DSN limits the number of communication passes per week. So all of those factors needed to be folded into the spacecraft design. Okay, so the first thing we took a look at was how to get the instruments, the altitude variability that they wanted to see. They wanted to get close to the atmosphere, and then they wanted to go out very far away from the atmosphere so that they could kind of see how the atmosphere changes as you move away from the planet. So we came up with an elliptical orbit. So an elliptical orbit basically means it looks like an ellipse, right, where the planet is on one side of that ellipse. So part of that orbit, that's the part where we go very close to the planet, and then we swing way far away from the planet. And so we were coming in, close to 150 kilometers, and then going thousands of kilometers out for the apoapsis, or the furthest away part of the orbit. In addition to that, swinging close to 150 kilometers is pretty darn close. You're actually grazing the top of the atmosphere going through there. But the scientists wanted more. They actually wanted periods during the mission where they would go deeper into the atmosphere. So we came up with what we call deep dip campaigns, which is where we actually change the orbit, where we move the periapsis, or the closest part of the orbit, deeper into the planet's atmosphere. So we actually started dipping down close to 125 kilometers, and we've gone even a little bit lower than that. And so we do that for 2 weeks, and then use our thrusters to pop back out to our nominal 150 kilometers. And the reason that we don't stay down there is because the drag at 125 kilometers is actually significantly higher. And so if you stay there, it will eventually pull the apoapsis part of the orbit down closer than the scientist wanted, and thus it'll shorten the lifetime of your mission. And so we'll only do that for a couple of weeks at a time. Also, when you're down in the atmosphere, there's a lot more variability, and it affects the spacecraft more, so you have to fire your thrusters more. And so from a fuel point of view, if you stayed at an orbit that was going all the way down to 125 kilometers, you're eventually going to have to use a lot more fuel to maintain your attitude position, and that will shorten the life of the mission as well. So we came up with what we thought was a good compromise. We'd stay in this elliptical orbit most of the time, and then every now and then we do a 2-week campaign where we dip deeper into the atmosphere to get some very specific measurements over some very specific longitudes of the planet. Okay, and so we factored all of the other constraints in and came up with the spacecraft design. Probably the first thing you'll notice if you're familiar with some of our previous orbiters all had articulating solar arrays. So the idea for those other missions was to keep the spacecraft body pointed fixed to the planet, and then articulate or use gimbals to actually move the solar rays to keep them on the sun, and move the main antenna to keep it pointed at Earth. So we flipped that around because we had a lot of instruments that wanted to look at the sun, and so we decided it was easier, since there were more instruments that wanted to look at the sun, to keep the body of the spacecraft pointed at the sun, and that way we could lower cost by not articulating the solar rays. And so we could have them fixed, which is a much cheaper solution, to the body of the spacecraft, and keep the body of the spacecraft pointed at the sun. And then because the DSN, we only had a couple of passes a week anyway, we said instead of keeping the solar array or the communications antenna articulated and always on the Earth, we would just slew the whole spacecraft during those couple times a week to talk to Earth. We'd just swing the whole spacecraft off the sun, communicate, and then turn back to the sun. And from a science point of view, that was deemed to be kind of an acceptable compromise. So that allowed us to reduce our costs. We didn't have to have as many gimbals. And instead, we took the couple of instruments that wanted to look at the atmosphere, and we put them on a gimbal. And so you can see down at the bottom, there's what we call the articulated payload platform. So basically a platform that we have a set of science instruments on with a 2-axis gimbal on there that we could articulate or move around to get the payloads, those particular payloads, pointed at the part of the atmosphere they wanted to measure as the spacecraft stayed fixed pointing at the sun. So it's a solar array powered mission, like our other Mars orbiters. And so we have to, from an engineering point of view, we have to accommodate the fact that Mars is further from the sun, about 1.6 AU. And so we actually have to put more solar cells on there than we would if this were an Earth orbiter. And then also the intensity is a little bit less because you're out at 1.6 AU, and it's also colder. And so solar cells react differently in those conditions. So we've actually done quite a bit of testing at those conditions to make sure that we understand how the cell performance is different than cells used in typical Earth orbiter applications. And then we used a hydrazine-based system. So our propulsion system, the rocket engines that we use, basically use a single propellant. And we use those to get into orbit, and then we use reaction wheels to actually articulate or move the spacecraft to get it pointed to where we want to go. And then we use our smaller hydrazine thrusters to, once the wheels spin up to a high level, to hold the spacecraft still as we, what we call desaturation, or turn the wheels and despin them back down to zero. And so that was a key part of the design. And then the other thing that I probably didn't mention is one of the other science instruments that they wanted to fly was a magnetometer. And one of the things magnetometers measure, right, is metal. And so they want to be kind of as far away from the spacecraft as they can be, so that measurements of the metal inside the spacecraft don't affect the measurements they're trying to take of the magnetic field generated by the solar wind coming in and some of the residual magnetic field from the surface of Mars. And so we looked at putting booms on, but they're kind of expensive and kind of a pain. And then we did some measurements that said, look, if we just put them on the ends of the solar array and then actually put fixed platforms or fixed booms on there to get them even further away from the solar arrays. So you can see those little triangular pieces on the end is where we put the two magnetometers. And so we put one on one side, one on the other, so they can get kind of a little bit of stereo vision and some redundancy in there. And then another instrument was called the Langmuir Probe Waves, measures some of the electromagnetic fields around Mars and as the solar wind interacts with the atmosphere. So those are two, looks like TV antennas on the top there, and those actually deployed as well. So basically they're compressed inside a canister, and then you fire them, and they actually just kind of shoot out in a deployment mechanism out away from the spacecraft. So like antennas, they pick up the electromagnetic field. So those were the kind of engineering design issues that we kind of had to figure out as we designed the mission. How do we package all this thing while leveraging all of the heritage that we had from our previous Mars orbiters? And so so that was the design of the spacecraft. And then once we had a solid design down, then kind of came you know, a series of reviews to make sure that everybody agreed that that was a robust design, that everybody thought this was going to work. And the process that we used is a fairly typical one in the aerospace industry. So we start with a system requirements review, and that's where we wanted to make sure that the scientists, the engineers, and the program management all understood what was our mission, what we were trying to accomplish. Did we understand our requirements so that when we started designing the spacecraft, we were all designing to the right set of requests from you know, from the science team and NASA. So you go through a science requirements review, and then we spend about a year after that doing a preliminary design, and then we have a preliminary design review, and that's where we say, here's our design. Does it meet the mission requirements? Does it meet the schedule? Does it meet the costs? Is everything holding together? And at that point is where NASA kind of comes in, takes a look at it, make sure that they've got confidence that you can pull this mission off and that the mission's going to do what they expect it to do. And at that point is where they actually transition from what we call Phase B, which is preliminary design, into Phase C, which is implementation. And that's where, in some sense, they say, okay, now we'll write you the big check for the large amount of money that it's going to take to actually build this thing. You got to pass your PDR. The next design review is called a critical design review, and that's where we've taken the preliminary design and actually gone down to producing all of the drawings, all of the circuit diagrams, all of the harnessing, where are all the blankets going to go, where do all the bolts and fasteners go. So basically the detailed design is like the blueprint of how to build a spacecraft. So it's everything you need to do that. And at that point we also got all our contractors on board, had all of our parts ordered, and then and basically started the process of making sure that everything was going to come in that we needed to actually build this thing. Once you pass the CDR, the next gate is your integration readiness review, and that's basically where you go through and make sure that everything you ordered, all your designs, all the piece parts are ready, have been delivered, and you're now ready to start assembling the spacecraft. And so you go through a pretty significant review looking at not only your readiness, but are your plans, your procedures, your personnel, your facilities, is everything ready to start actually building a spacecraft? And so once that's done, you start building it, you assemble it, you functionally test it, and then once the spacecraft is doing everything that it should be doing inside a clean room environment, that's the point where you now are going to go through your environmental tests. So you have an environmental test readiness review where you go through all your plans for how you're going to simulate all of the environments the spacecraft is going to see as it goes through a launch on a rocket and then goes out into space. And so we do tests like acoustics test, where we actually use loudspeakers to basically radiate the kind of sound levels that your spacecraft's going to be exposed to inside the fairing of a rocket. And it is extremely loud, and it can damage very sensitive components. So it's a very critical test to pass. We also did a vibration test on this, where we shook it like it is going to be shaken on the rocket. We do an EMI EMC test, which means turning on all of the radios, and also putting up simulated ground radar and radios that it's going to be exposed to both at the launch site at Kennedy Space Center and also during flight as the DSN beams radio signals to it and it beams radio signals back. And then the biggest test we probably do is called a thermal vacuum test. And this is where we take the spacecraft and we put it inside, basically you can imagine a giant thermos bottle, which is about 30 feet across and about 100 feet high. So basically it's a chamber where we flood it has hollow walls, and we flood the walls with liquid nitrogen. And then we also evacuate all of the air out there. So it's a vacuum inside, surrounded by liquid nitrogen, which takes the temperatures out to the cold of what space is like out near Mars. And then we actually have a series of very special lamps on top of the chamber, which will actually turn on to simulate the sun. And so we can actually simulate any intensity of the sun all the way from what it's like at Venus all the way out past Mars. So we tested MAVEN, and it was all ready to go. And so you got some pictures here. This is the proposal team. So again, we had to convince NASA to choose us. It's probably one of the things I should cover a little earlier. Even though we had a great idea, working with CU and Goddard and us, we had to convince NASA to choose us out of a competition where we had a lot of other people out there with other mission ideas that they wanted to do. And so there were a whole lot of competitors out there. We put a good proposal together, and NASA chose us to go. So once we're done with the environmental test, we actually have to get the spacecraft down to Florida. And from our facility down here in Waterton, Littleton, Colorado, basically, we put the spacecraft in a big box. You got to keep the spacecraft warm. You got to keep the spacecraft clean. And so we actually have a nitrogen purge in there to keep any dust from getting into the container. We have heaters and air conditioners to make sure the temperature is controlled inside that box. And then because we're a government program, government's got a lot of big planes, and so we hitched a ride on an Air Force plane. They were very happy to give us a ride from Buckley Air Force Base and out near Aurora, and fly all the way down to Kennedy Space Center down in Florida. And so we just put the box on the plane, huge military cargo plane, took us down there, took it off, and got it in the clean rooms down there. We did processing down there, which included final deployments, and including deploying our solar arrays. That's one of the more fun tests to watch. These arrays are huge, and they're folded up against the spacecraft, and then we fire the deployment mechanisms, and these things actually deploy in the clean room and make sure that there's going to be no issues when they deploy in space. And then we also do our other final checkouts, make sure everything's working right, including loading rocket fuel on board the spacecraft. So people have to dress in special suits in case there's any spills of the hydrazine rocket fuel, which is very toxic. And we load the spacecraft and get ready for launch. And then once it's all loaded and ready to go, we actually get the fairing over, which is the nose cone of the rocket. And that's brought over from the United Launch Alliance, ULA team, because since we're going up on an Atlas rocket. And another Colorado connection, since ULA is headquartered out here in Colorado. So a lot of Colorado folks down there getting ready for launch. So you can see the spacecraft in the middle. You bring the two sections of the nose cone together, and then secure it, and then you actually take it out to the rest of the rocket, which is out at the pad, and use cranes to actually lift the whole thing up to 10 stories or so up to the top of the rocket. It's a little nerve-wracking when you're a program manager. You spent so many years and sleepless nights trying to get this ready, and then you see your spacecraft swinging on the end of a cable that looks way too thin up about 100 feet above your head. But we had a successful launch, November 18th. The rocket gave us a great ride, a beautiful day. We launched on the very first second of the very first day of our launch period, and we were on our way to Mars. It took us 10 months to get out there to Mars, and then the next critical activity was getting into orbit, because we had to fire our rocket engines at a very precise time to get captured into orbit. And if we didn't, if for some reason those rocket engines didn't work, they didn't fire at the right time, we would fly back, we would fly past Mars, and then we wouldn't have another opportunity. Basically, we'd fly past Mars, and our orbit was such that it would have been extremely difficult to try to figure out how years and years later we could ever get back to Mars and try again. So very critical activity, needed to make sure that it was going to work that first time. But on September 22nd in 2014, you can see the control center as we got confirmation that we were successfully in orbit. Once we were in orbit, then we deployed our boom with the LPW antennas. The articulated payload platform was also another deployment that we had to do to pop that boom out so we could start articulating those science instruments. So we did some initialization activities, and then we spent 1 Earth year doing our primary mission. That was very successful, and then we started getting, because the spacecraft's doing so well, we got another, our first extended mission. We're now on our second extended mission, and we're starting to look ahead towards a third extended mission. So the spacecraft performed extremely well and is returning phenomenal science data. And if you do well and you get good science data and your scientists publish all kinds of paper, you get to be on the cover of Science magazine. So I'm not a good enough scientist, just an engineer, so I can't explain all the science that's come back. But I can tell you the response back from the science community to Dr. Joukowsky and the rest of his science team's papers has been really, really phenomenal. Extremely great science has been coming back from that. The biggest, of course, being that they now have kind of taken all the measurements to have definitive proof that indeed it's the solar wind coming off of the sun that over time has stripped the atmosphere and has it basically causing it to be lost into space. So the solar wind comes in, and so what they believe now is that Mars, early in its history, had a magnetic field, but when but because it was a smaller planet, the core of the planet cooled, shutting off the magnetic field. The magnetic field is what kind of helps protect the planet from the solar wind. Without that magnetic field, the solar wind had a much more dramatic effect on the atmosphere and started causing it to be lost to space. And so they now have all kinds of measurements showing that. And in addition to that, they've announced science results such as seeing aurora on Mars and seeing different dynamics in the atmosphere than they had expected. And as a bonus, soon after we got there, there was actually a comet that was flying by, that was on a trajectory that would have it fly by Mars, Comet Sighting Springs. And so we had an opportunity on MAVEN to actually take measurements of the comet and the comet's effect on the atmosphere of Mars. And so we got a lot of good bonus science out of that. So anyway, a very successful mission. The scientists seem very happy with the results, and it's still going strong. We just finished another deep dip. I think it's our 7th one, just about a month ago. And spacecraft's doing good. One of the things that it has on it is also a relay capability. It's got a UHF radio, so it can actually be part of the relay network that is used to talk to rovers on the surface, rovers and landers on the surface, and communicate their data back to Earth. The majority, of course, being done by MRO and Odyssey, but should it be called upon, MAVEN has that capability as well. So that's MAVEN from an engineering point of view. Some of the challenges that we had, and some of the history of getting the spacecraft from the design phase all the way out to returning data from Mars. So are there any questions?
If you have questions, please go ahead and type those into the chat. I have a question for you, Guy, and that's in relation to the solar arrays. They are bent at a maybe 20% angle. Can you comment on that and the decision that went into having those in that sort of a configuration for the deep dips and how that affects the flight of the spacecraft?
Yeah, that's a great question. So basically, as we talked about, the spacecraft actually dips a little into the orbit, or into the atmosphere every orbit, and then we've got those deep dip passes where we actually go deeper into the atmosphere, and so the atmosphere is actually pushing on the spacecraft. And so one of the things we wanted as engineers, we wanted to make sure was that the spacecraft, due to the atmosphere kind of pushing on it, going through the drag of the atmosphere, didn't start tumbling. And so we wanted to come up with a design that would be stable, even as it's going through the atmosphere. And so one of the things that we looked at was, you can kind of imagine, if you've ever played badminton, you look at a badminton shuttlecock, and it basically has a swept back outer shape to it. And so what we did is we took a look at the solar arrays, and we did some calculations that showed if we took the outer panels and swept them back by a certain number of degrees, that it gave it inherent stability as it moves through the atmosphere. So basically, the back of the spacecraft would be going into the flow, and then those gull wings, as we call them, the swept back solar arrays, would actually give us some stability. So if the start moved one way, the atmosphere would naturally push us back to having the center line of the spacecraft going through the atmosphere. So that was one of the reasons that we designed it to have the solar arrays looking like they do, being swept back a little bit. Also, it makes the spacecraft look a little bit cooler. So.
Great, thanks. We do have a few questions coming into the chat here. The first one from John Heasley is, what science would you like to see done on future Mars orbiters?
Yeah, I think we've now kind of gone through our survey, right? We've all of these spacecraft together have given us a lot of information about Mars, about kind of its history. We now have a good sense of, here's what the atmosphere was like, and when there could have been water on the surface. We know from our surface observations, both from orbiters and landers and rovers, that kind of where the interesting areas on Mars are. One of the things we did on Mars Phoenix is we landed on Mars, at a place, and the orbiter said, you know what, we think there's ice buried close to the surface. And Phoenix landed and dug down, and just a couple inches below the surface was huge sheets of ice, basically a whole frozen ocean underneath a little bit of dust. And so we know that there's water on the surface of Mars today in the form of ice. MRO has actually detected that there may be flows of ice, flows of water coming down the sides of craters that evaporate, but flowing water maybe even today. And so looking ahead to what kind of science we want to do, I think it's going to those interesting places now that we've kind of done this global survey, and actually getting down and getting samples of those interesting places so that we can take a look at them and really find out, is there life? You know, is there evidence of past life on Mars, even if it's microscopic? Is there any life on Mars today? There might be microbial life still living in those regions where there's freeze-thaw cycles. So there's a lot of really interesting places to go on Mars, but the next big science thing is kind of to go to those places, and most scientists would agree that if they could do it, is to get samples from Mars back here to Earth, so that we can use the much more extensive laboratory capabilities back here to measure them, analyze them, and really determine, was life ever on Mars, and is it there today?
Great, thanks, Guy. Another question from Michael Hoist is, where en route was the satellite released from the mothership? And by that, I imagine he means that payload fairing and maybe the second stage Centaur. You could comment on those if you're...
Yeah, so basically it's a fairly quick process. And so basically the Atlas launches us, and we actually have to kind of swing around the planet. And then we get another firing from the Centaur upper stage. So it's only an hour and a half or so before we're actually released from the launch vehicle. And so it's very close to the Earth. And so we're released very close to the Earth. The spacecraft immediately deploys its solar arrays, gets them on the sun so that we start getting power, and then starts talking to the ground. So we were down in Kennedy Space Center waiting for that signal that says we got signal from the launch vehicle that says we're released. And then we started waiting for the signal from the spacecraft that says my solar arrays are deployed, my radio's on, all my systems are working. All of that takes place within the first couple hours of launch.
Great. One more question from Dave Dooling, and that is, it's more of a comment, but I'll try to morph it into a question, is details of the internal structure of the spacecraft would make a good lesson. In 2015, we had summer campers build a quarter-scale model of New Horizons, and they learned a lot about systems design. Do you know of anything similar to that, Guy, either for MAVEN or other missions that Lockheed has worked on, where you kind of map out some of the internal structures?
Yeah, and so all of our, of course, all of our design, is now on the computer. So when we do a structural design, we actually model the entire structure inside computer programs. And so we've got 3D models of basically everything we build. But sometimes 3D models and analysis aren't enough. Is we want to make sure that we understand how a structure is gonna behave. So we don't just build the structure and then bolt everything on and go. We actually do what we call a static loads test, where we'll actually build the structure, and then we'll put it in a chamber, and we actually have devices that actually apply stress to that structure in very certain points all over the structure to see how the structure is going to react. And so we want to make sure it's not going to crack, it's not going to have any vibration modes that we're not expecting. And so we do a very extensive test on that before we take the structure and then turn it over to our integration team to start bolting all the other pieces on. And one of the other tests that we've done is on Mars Phoenix. We were a little concerned about how the whole structure and propulsion system would function as we fired the rocket engines that would slow us down as we descended to the surface of the planet, of Mars. And so we'd done a lot of analysis and everything looked good, but because there was, this was such a lot of nervousness about, are you sure all your analysis is going to be correct and that everything about the forces that are going to be on there, we decided to actually build a complete structure, put it with a complete propulsion system in a test vehicle, and then load it with hydrazine and actually fire it here in our plant down in Littleton, Colorado. So we actually did a live fire of a propulsion system just to make sure that we understood how the propulsion system would work and how it would interact with the structure to see if there were any modes or vibrations that we needed to take care of that weren't accommodated in the analysis.
Excellent. A couple more questions, Guy. One from Carolyn. First of all, she says, congratulations on your promotion at Lockheed Martin.
Well, thank you. I appreciate that.
Secondly, do you see MAVEN helping the science from the landers and rovers? For example, using MAVEN to study the solar wind effects on the surface so we know where to land the rover/landers. If so, do we have any plans to study the effects of the solar winds on the planet?
Yes, and that's one of the things that I think the scientists are most excited about, is because the spacecraft is doing well. They would like to keep it alive as long as possible because, as you guys may be aware, the sun has a solar cycle. So what is it? Every 11 years, it kind of goes through an active phase and then a very passive phase, and then a very active phase and a very passive phase. So basically, being able to take data over that complete solar cycle will give them a very complete understanding of how the sun interacts with the atmosphere of Mars. So they're very interested in getting more data, especially through the whole solar cycle, and also with any flares or those kind of short-term activities from the sun. We are very interested in sending astronauts to Mars, and so how solar flares, especially, how much protection the Mars atmosphere will provide to astronauts on the surface is something I think NASA is interested in, and so certainly data from MAVEN will be useful for that. But also the fact that we are taking data to help understand the history of Mars by being able to come up with very complete models of when the atmosphere was warm enough and thick enough to support oceans on the surface. That helps future missions down to the ground, rovers, to know where in the geologic strata to look. Where is it most likely we're gonna have times when there were oceans down there, and so they can help target some of those investigations. So look at the most interesting times in Mars history back when it did have oceans, rivers, and lakes.
Yeah, and one other comment I would make about that is that the Curiosity rover does have a radiation detection instrument on board, and I know the science teams from the rover and the MAVEN group are working right now analyzing a large X-class solar flare that erupted off the surface of the sun earlier in September, and seeing the effects and correlating the effects that each of those two missions witnessed.
Yeah, that's a great point. As one of the beauties of the Mars program is that you have multiple spacecraft all taking science data, right? So you can correlate, data from one mission and the other, and kind of get a more complete picture of going on, as opposed to the fact we've only got Juno and Jupiter right now. So the fact that there is a complete Mars program, there really is a lot of benefits from MAVEN talking to the scientists on MRO, who are talking to the scientists on Curiosity, all of them sharing data to get a very complete picture of what Mars is like.
Great. Jeff Nee has asked, he says that slide 14 is very interesting, seeing the antenna bare. What is the covering and how does it help the spacecraft? Is it the same case for other missions like Juno?
Yes, actually, if you look at, here, we'll bring up the spacecraft again so people can kind of see it, but basically what you see is it's got a covering on there, and that's actually just a thermal blanket. So it's a blanket. What we want to make sure is that we keep the structure of the antenna thermally, basically thermally stable. We don't want gradients across the different parts, because then the material might distort a little, and if you distort an antenna, you change its pattern. So one of the things we wanted to do is put a blanket on there to keep the heat of the antenna uniform, or the heat underneath it uniform across the surface of the antenna. It also helps keep the antenna warmer, and so to keep it closer to inside the middle of the thermal properties of the material we used. And so so basically we tend to cover a lot of very sensitive, or a lot of areas with thermal blankets to kind of keep that thermal uniformity across the vehicle. And so that's actually, there's silver across there and gold. This is actually an illustration. The gold is also thermal blanketing. It's actually silver in the real spacecraft. But again, kind of doing the same purpose, trying to keep the heat inside there, because out at 1.6 AU, it's a lot colder than it is here at 1.0 AU.
Great. We also had a resource shared in the chat if anybody's interested in looking at that, about student activity on designing a mission. It's called Mars Bound. It's out of Arizona State University. I've used that in my own programs, and
great.
It is a great set of curricula. And then we have one final question here from Mark Baker, which is, with drone technology being so well developed, do you foresee any mission in the near future that may utilize orbiter-controlled drones, especially for atmospheric studies?
I do. I think that that's kind of the next mission. The next set of missions, I think, are going to be doing some more ambitious stuff. If you look right now, NASA is considering flying a helicopter drone on the Curiosity rover. They haven't made a decision on it yet. There's a lot of work that needs to get done as kind of doing this demonstration. So maybe they'll do it, maybe they won't. But they're actually considering carrying one and then deploying it off of the Mars 2020 rover. And so that would just kind of be a demonstration. But the idea being, we think drones and aerial vehicles, whether they're balloons or whether they're helicopters, whether they're planes, we think having mobility on Mars helps do a great part of a very valuable set of science goals. And so looking ahead over the next period of time, I think there's going to be some missions out there that's going to do some things like that, where they get balloons or planes or helicopters doing more stuff, flying around and getting more and different coverage of what you can see on Mars.
Excellent. Yeah, I'm sure Lockheed will be right there at the forefront of all of those technology demonstrations and development.
Yeah, we're helping out right now on Mars 2020, so we're very excited about that. We're actually doing the entry system, and we've been working with them on some mechanism, the deployment mechanisms, some ideas for a deployment mechanism. And so we'll see where NASA goes with that, but we love Mars missions, and very excited about working with NASA on what's possible.
Great. Jeff also commented that he's very interested in the science cover image. Is it available in any other format, like a poster, PDF, or perhaps even a downloadable 3D model? Jeff, I can get you some of those products in highest resolution available. I have those for you.
Dr. Joukowsky probably has a bunch in his office. So
I think he has a framed one, I'm pretty sure. So. Guy, thanks a lot for doing this presentation. This was wonderful. And from me, I'd like to thank you for the job you did on the MAVEN spacecraft, because that's supported my work here over the past 7 years at LASP, doing communications for the mission. And if we didn't have a successful spacecraft, I wouldn't be doing as well on the communications end. So I appreciate it.
Communications wouldn't be as much fun if we didn't have the successes to celebrate. But I also want to thank you, Tom, for all the work you did on MAVEN. You were a huge piece of helping us, get this mission to where it needed to go and getting our story out for everyone. And that's what it's all about. The taxpayers pay for this. We really want to make sure everybody knows all the great things that not only MAVEN do, but NASA and CU and Lockheed Martin. So thank you.
Okay, thanks everyone for joining us. Look out for our next announcements. We'll probably have a talk in maybe in November, or if not, it'll probably be after the holidays, but keep your eyes peeled for the notifications. And thank you very much. We had one final comment. Please send our congrats to all the team members of MAVEN good luck on the InSight launch in Mars 2020, as well as other programs within SES. Foreman from a former MAVEN Lockheed Martin, or LMER.
Fantastic. So thank you very much for that.
Take care, everyone. We'll see you next time.